So we're presenting Delta Graph, which is a Haskell-based graph processing system for update-intensive graph programming. And we focus on an update-intensive setting, particularly because updates are difficult, right? And they're in lots of these big graph systems. For example, Twitter. During these breaking news events, there might be lots of updates happening, lots of these new following relationships, and they're becoming in rather fast. So a very responsive system is desirable. Also, we have these general benchmarks which are written for graphs, and they often involve construction. So construction, which involves updates, is part of the benchmark. So in a nutshell, right, Delta Graph offers a pretty conventional programming model. So Atom is our empty graph. We offer the basics, right? Insert node, insert edge, delete node, delete edge, all the way down, mapping, folding, looking up, nodes and edges. Under the hood, Delta Graph does have a somewhat unconventional runtime semantics. Specifically, which we'll go into later, has in-graph memoization and the local propagation of graph updates. So we'll start off looking at a pretty simple graph programming example. All right, so we create this this graph. We insert some nodes, insert some connecting edges. Right, so we step through this. So this is what you kind of the logical view of the graph would be in the standard graph processing system. You step through, nothing surprising, right? So now let's see what a runtime behavior of Delta Graph might look like. So you create this first node, I'll call it the root. And unlike in standard graph, in a standard system, which inserts a node and leads to topological updates. What the evaluation does here in Delta Graph, it immediately returns to the next line. And all it does is insert this, it adds one extra element at the root node, which we call the delta list, this kind of extra component. And it's the memoization of the request to insert node 2, right? Right, so we call this a delta list, and we're going to kind of list some benefits throughout the talk here. So this is, reactiveness, right? So that's good in these systems. So the same thing happens with node 3, right? We can memoize that intention. And Delta Graph is a non-deterministic system. So at any point throughout the execution, we can propagate some updates. We can realize them. So for example, right, we can realize this new node, node 2, while removing it from the head of the list. So we go through, we add some more updates, all memoized, right? Non-deterministically, we can again decide to perhaps realize some of these updates, right? So if we realize all of the ones that were in the delta list there. And we continue on, right? And so delta lists are distributed in that every subgraph of the graph, right, has its own delta list. So this is friendly for parallelism. So for example, right now, if we're about to insert an edge, 24, so we can memoize that at the root, and also node 3 could propagate not propagate, realize this node 4. And it's non-deterministic. So at any point, these propagations and realizations can happen. Let's see. So as long as the logical view of the program is preserved, right, we can freely do these propagations. Also, the representation I'll go into more later, but we do have to explicitly show back edges in the system. So I'll show those with the dotted line in the next couple slides. So delta graph supports the optimization of this delta list. So with this example, we have kind of the same graph as last time, except we have two mapping intentions that are already memoized at the top. So delta graph can see this and pretty simply, just merge them into one update. So that's some kind of, little cheap trick here. But this also works with, for example, adding a node and immediately or soon thereafter deleting it. So those two obviously cancel each other out. And this we call prenatal optimization. This is benefit 3. So one challenge in developing a lazy propagation system is representation. And the choice that we've made or other choices really matters. So what we ended up with is graph overlays on inductive trees, which means if you look at a graph, right, you can kind of squint and see a tree-like structure. Every edge that did not fit into that tree structure will have to be a back edge or a cross edge. So explicitly mention which nodes it connects to instead of just induction. So as mentioned, these delta lists are just decentralized, right? So each node has its own local list. So local propagation can happen. Right, so, and propagation only involves the children, right? So when node 1 right there propagated down, it only involved node 2 and 3. When node 3 propagates, for example, it'll only involve node 5. Right, so that's another benefit there. Ordering is pretty important in this system. So there's implicit chronological order with these updates. So for example, this program here is quite different than one if we would swap x2 and x3. So if we first mapped over the graph and then we inserted node 7. For example, node 7 would turn to node 8. Oh, sorry, it wouldn't. It would, yeah. Right now it changes to 8, but it wouldn't. Right, so it's quite different. However, we could indeed, in the ordering of the delta list, we could decide to actually swap them, which may lead to optimizations. The only thing we have to do is just we have to make sure that we do indeed account for the actions that the update would have made. So in this case, when we do swap the insertion and the mapping, we have to make sure that we do apply that function while the mapping jumps over the insertion. So this is part of the prenatal optimization that I mentioned. Deletion is quite tricky in this system. It's led to lots of maybe headaches, I would say, in designing it. Why it's tricky is because we use inductive trees. So we're going to get some sort of orphans, right? You delete a node. Right, so if we have this deletion node, that's delete node intention, which made its way down to node 1, it has a child of 3, right? So if we realize this update, we're going to be left with a what we call an orphan graph. Right, so this is something that was attached to the inductive structure, but it has hence been removed, obviously by deletion in this case. Deleting edges could also lead to orphans. What we can do with this, right? So if node 4 happened to have a back edge to node 1, we could remove this back edge and turn it into an inductive edge. So that's something easy we can do. If it didn't, which is unlikely since that's actually the node it was attached to begin with. We can propagate it up the graph towards the root and look for reattachment opportunities. So yeah, so we have this dual kind of direction of propagation in this system. So to experiment with our system, we have created a mini Twitterer application. So users are nodes, requests are, following requests are edges, right? So a following relationship is an edge. So we support new user requests, following requests, right? The removal of either of those, user lookup, and then the edge or the following relationship lookup. And the graphs we're running with these benchmarks are usually around 1 million nodes, 5 billion edges. In this presentation, they're all scale-free. In the paper, we look at randomly generated graphs and scale-free graphs. Right, so we're trying to build a system that's heavily reactive to updates, mutations in the graph. So that's kind of this first experiment that we run. When the update ratio is high, so this is increasing number of updates compared to lookups, we do quite well. So we're comparing against what we call standard graph, which is just a simple node edge representation, right? So the graph theoretic representation of just a list of nodes, set of edges between them. And then the FGL, which is a standard go-to graph library in Haskell, Airwig. So when plenty more of updates happen compared to lookups, we do quite well, which is what we would expect. However, some of you probably have a question, right? So when lookup is very high, we start doing quite well, right? So up is more reactive in this graph, right? So we kind of stop being that reactive when there are more lookups. So a lookup in this system is a single key lookup, right? So we are not that situated. We're not well situated for single key lookup. However, with lookups that are require more kind of structure, so for example, clique lookups, we have some structure encoded in this graph. Right? So edges are inductive, right? So a node, all of its children, those are edges, right? In the actual graph, the logical graph. So with that, with clique lookup, we can do a little better actually than either of these other systems because of the structure encoded in our representation. So as mentioned a few times, a representation is geared, or it allows for some parallelism, right? So in this experiment, we only try some kind of simple parallelism, right? So every lookup that happens, you can also propagate, right? So that's not what I showed, but well, I showed something else. But when there is a lookup, some of these child nodes could also propagate as well. So there's still room for improvement. However, when there are roughly the same amount of lookups as opposed to updates, which is when we do parallelize, we can get some speed up. Other areas, there's really not that much opportunity, since either too many updates are happening compared to lookups, or not enough lookups are happening compared to updates. We do explore some other parallelism opportunities in the paper. Yeah. So this last experiment I want to talk about is one where we tried opportunistic computing. So delta graph is uniquely situated to take advantage of idle time in a computation. So we introduce varying arrival times of updates and lookups. So there's some time in between this system. So we have one thread that's handling requests and another that's propagating in between these requests. So if we look on the right here, our opportunistic system can, if we have more time in between arrivals of updates, we can do things like this prenatal optimization. So we can optimize, or what we call normal form in the paper, optimize the delta list. And we can respond quicker than if we do in the normal system. However, at some point we just get we get a little too saturated, and I think it's just I think there's an opportunity here because our system is it gets too saturated. However, I think with some better maybe some programming techniques or something, we can take a look. So if we are getting too saturated, right, just stop this other thread that's doing the propagation and just handle the lookups. Related work, so lazy evaluation, so laziness is a fundamental feature in functional languages, right? Computation-centric laziness, right? So lazy evaluation, incremental computing, and self-adjusting computation. So these are what we call computation-centric laziness. So memoization is done over a call graph or order the structure of computation. What our system is more data-centric laziness, right? So the memoization happens over the actual data itself, not over any algorithm or computation happening. Also, inductive graphs in general, there's a lot of work that's been done. The Olivier and Cook structured graphs, which uses a parametric high-order abstract syntax approach, and the functional graph library by Airwig are the most influential to our work. All right, so in summary, we're presenting a graph processing system with reactiveness to updates, parallelism friendliness, prenatal optimization, and local propagation steps. Thank you.
Questions? And if you could stand when you ask a question, please.
Very good. So is this persistent? I mean, the graph that you're building this way, is this a persistent data structure, or do you do mutation?
It's persistent.
It's persistent.
Yeah, oh, sorry, I should have said this. This is all in the context of pure functional languages.
Yeah, and my other question is, do you support cyclic, like directly cyclic stuff?
Directed acyclic.
No, like directed cyclic, so you can.
Oh yes. Yeah, so that was the point of the back edges and the cross edges, right? So they can definitely point back. Of course, there's no induction backwards, right? So that is why we need these kind of back edges, and that is why I think graphs are hard in general in pure functional languages. You can't represent these. You can if you do this parametric high-order abstract syntax. You can't. And also tying the knot. However, you can't dynamically tie the knot in these systems. Yeah.
Ivan Miljanovic, I'm just wondering, in terms of your representation then, so you're storing it as a spanning tree with the extra back edges and the cross edges?
Can you repeat that? Or
just to clarify, your representation is a spanning tree with extra back edges and cross edges stored at some of the vertices?
Correct, and the extra delta list component.
Okay, so is it like just directly a directed graph then?
So in the library, in the paper, we don't tackle directedness. However, in the library, we do offer that.
Okay. And are you allowing multiple edges and loops, or is it just simple graphs?
Multiple edges and loops, like with two edges.
Between two vertices?
I haven't thought of that. I don't see why.
Just wondering on the complexity of your model here and how far you...
Oh yeah, I don't see why it wouldn't be able to support that. It does support that. Yeah, of course, one would have to be inductive, one would have to be a back edge, right? Yeah.
Yeah, I've got two questions, so I guess I'll start with the simpler one. So when you create a node, you give it the piece of data you want to be at that node.
Yes.
What happens if you create two with the same piece of data? Because that seems to be the only way you have of identifying nodes. So is it
Okay, so in this representation, I only represented them with the key, right? So there is actual payload that goes along with it in the library and in the paper as well.
So if I create two nodes with the same key, do they just, what happens?
Yeah, so we have an operational semantics that goes along with this, and that's actually an error in the system. So
Okay.
yeah.
And the other question is, you mentioned there was that it's non-deterministic.
Yes.
So before you add in the parallelism, where's the non-determinism?
In the implementation or in the more theoretical part of in the semantics? Or?
In the implementation.
Yeah, so good question. That's I think that's a design decision actually, and I haven't decided the best way to implement it in this library right now. However, there are basically two ways to go about it, right? There's this opportunistic computing part that I did, where one thread is just in the background propagating, trying to optimize some stuff. There's also the more pure way of doing it, where you just piggyback on a lookup, or you piggyback on insertion, or you basically, whenever a user interacts with it, you also look like, oh, is there any other things I could be doing now too? Yeah.
So that's, if you don't have the parallelism, that's where the non-determinism comes from, the fact that there might be lookups happening in.
Yeah, if you're doing some concurrent stuff. Yeah, I wouldn't say it's necessarily parallel. Yeah, but concurrency.
Okay.
Michał Guide, I have one question. It is common for algorithms on graphs that compute something over the whole graph and interactions to either exploit the least fixed point using some kind of topological ordering or maximum flow. Do you support this kind of optimization?
In general, we have not gotten to the point yet where we support these more advanced queries or lookups or anything like that. Yeah, that is definitely part of our future work as well. Yeah.
Do we have any more questions? Okay, let's thank the speaker once more, please. So that concludes our